Okay, thanks. And so I guess I should introduce myself too. I'm Afonso Bandeira. I'm a professor of mathematics here at ETHZ. I've been here for a year and a half. And yeah, I teach last semester. I taught maybe to some of you. I recognize some of the names, complex analysis. I teach also a master's course on mathematics of data science, which if you enjoy this course, you should look into taking that later on. And so let me tell you a bit more about what this course is going to be about. So the idea here is to introduce, this will be a mathematical course. So the goal here is not to teach machine learning per se or from a user viewpoint, right? For that, there are actually many courses, in particular in computer science and so on. The goal here is a mathematical course. So we're going to explore mathematical concepts that appear, are needed, or are part of machine learning, or are used to understand algorithms and techniques in machine learning. But the main focus is definitely mathematics. So the idea is for this course to be accessible for second year, fourth semester students, right? I know quite a few, not everyone, but a good percentage of you are second year, fourth semester students. And so it's meant for the course to be accessible with that background. So it has minimum requirements. It does require a working knowledge of linear algebra, but this is something that you should all have. And the main challenge actually in designing this course was the fact that you are taking probability at the same time. And so for almost all the first half, we don't actually use any probability. And then in the second half, some probability is used, but by that point, you'll have learned already these things, and it's rather simple concepts in probability, right? Most things are sort of finite and discrete and so on. But as this is the first time we're teaching this and trying to teach this with these requirements and sort of simplifying the arguments or not, and so on, feedback would be, I mean, feedback is always extremely welcome, but now in particular would be extremely useful. So if you think something is going too fast, too slow, you want to see something that is not covered in class and so on, please do write us either on the forum or email. And there is a link for a Google Forms for where you can send feedback. Okay? And so please let us know what you think about the speed and so on, and in particular is the background. I mean, we were quite careful not to have any requirements, and however, it is required a working knowledge of linear algebra and sort of mathematical maturity in the sense of understanding and being able to construct proofs of theorems and mathematical statements. It is a mathematical course at the end of the day. We'll have theorems and we'll have proofs. Okay. So the homework is the homework will be posted on after the lecture, so maybe on tomorrow, so on Fridays, and then will be discussed on the exercise class of the Friday following. So if you would like feedback if you would like to solve the homework and you would like some feedback because you're not quite sure if you're solving it right, or you want to know the level of detail, things like this, you're welcome to submit the homework to your to the TA that's giving the exercise class that you signed up for. Okay, and each TA will tell you how to submit the homework. However, you don't have to, as the homework doesn't count for the final grade. So the final grade is the exam that counts. But if you would like feedback, you're very welcome to send them, and the homework questions will be discussed during the exercise class. So there are lecture notes for the course. I'll do my best to finish writing the lecture notes. So I'm covering, as Nikita said, roughly the first half of the course. I'll do my best to write the lecture notes before and put them available on make them available on the forum or on the website a day or two before the lecture, and then try to update them afterwards. Lecture notes are sort of about what you plan to say, and afterwards I'll try to edit on what I did say and what I sort of wish I had said. And so I'll try to update them rather frequently so that you can just follow the lecture notes. It should have all the material. In particular, I mean, I can give some other literature and references and so on, but I really haven't found on sort of the level that we want to take the course, and especially as it should be very mathematical, I haven't found any reference that is able to do this requiring sort of with minimum prerequisites as we intend. So we didn't find quite any perfect reference for this, and so we'll really have to rely on lecture notes this time and not just follow a book. And, On the lecture notes, if you've already seen, so the lecture for today was already there. I'll try. I mean, not all topics in the course are susceptible to this, but I will try throughout the lecture notes, and Nikita as well when it comes to his half to post challenges. So sometimes there's like a simple theorem and proving it will be a challenge, or there was a bit about k-means and there were some challenge like try to prove this, try to prove that. These are a little bit different in spirit to homework questions for a few reasons. So one is the difficulty will be sort of have a much higher variance. Some might be very easy, some might be very hard. There'll also be challenges that are sort of not just mathematical. I decided to call them exploratory challenges, but it'll be more how would you try to solve this problem, right? And not necessarily like precise mathematical questions. While the homework questions are more, precise, sort of regulated difficulty and so on, much closer to what an exam would look like. It doesn't mean that sometimes we might not make a homework question something that was a challenge in the lecture notes or vice versa. And so for questions, I highly recommend using the forum. So it's very efficient in the sense that you ask a question, all three of us and the teaching assistants can see it. We can all reply. You might, two of you might have the same question. You see it there. We sometimes get interesting discussions going and so on. So please make use of the forum, especially in these times where we can't do this, at least not yet face to face. It's important to have as much interaction as we can possibly create, and the forum is a good medium for this, I've found. Okay. So before I start with talking a little bit about the material that we're actually going to cover, I want to ask if you have any questions first. I just saw one question on the chat. No, the exercise classes will not be recorded. So the exercise classes will mostly cover, almost exclusively cover the homework problems. So you'll have access to homework problems, but there's no plans to record the exercise classes. Again, the exercise classes are most useful if they're as interactive as possible, and yeah. Recording tends to create a certain inertia for a lot of interaction. And so we're hoping that this way the exercise classes are a lot more interactive. And to ask questions, you feel free to unmute yourself right on the chat. Since there's a few of us here, when it's just one teaching, it's hard to keep an eye on the chat. But when there's many of since there's three of us here, it's very easy to look at the chat. But feel free to unmute yourself. Please interrupt, ask questions. Okay, so if there's no questions, then I'll start talking a bit about what we'll actually cover. Okay, and yeah, I would like to say also that this is also a good point, which is if you can, or at least some of you leave your camera on, that's very nice because it's much nicer to teach with seeing some people in front of you than a computer screen with just names. You don't all need to do it, of course, but if a few of you do it, makes a much nicer experience for one when it's teaching. So thanks to those of you that left your camera on and just encouraging some of the others. Okay, so this will be about mathematics. And if you can't see the screen or there's any technical issue, please let me know. Okay, and so we'll sort of separate it into four topics. Okay, and so in the next half hour, I'll try to explain what the goal is among those topics, or sort of in four sections. And I'll mainly teach the first two sections, and then Nikita Zhavotowski is going to teach the other two. So the first one will be what's known as unsupervised learning. Okay, so the idea here is that it's sort of, as the word is suggesting, is learning in an unsupervised way, but what you should think is sort of exploratory data analysis. So maybe you get points, let's say you get x1 all the way through xn, points in the dimensions. And now you want to learn something about these points, right? Maybe they are like, let's say they are in 2D, right? You get some points, you draw them. If you're lucky enough to be doing something only in 2 dimensions, you can actually draw them. If they are in dimension a million, then you'll have more trouble, but you get points, endpoints in the dimensions, and you want to know what can you do, right? What can we do? Okay. And so you don't know, you maybe go and sample the genomes of all the species of say microbes that live in some sample that you're interested in, or you take genomes of many different people or a data set of any type, right? Sort of features about some, in this case would be each microbe would have many features, and D would be sort of the features and the different samples you got. And so what do you do in a situation like this? You're starting with data points you don't know anything about your data. And I would say that there's sort of three things that you can do. Right? And one is sort of to try to model, right? To try to model the data. Right? So this would be sort of attempt number one. You would say, oh, I think the data comes from something like a mixture model of some type. Okay? Or the data comes via the following process. I first, each of these, say, microbes belongs to a certain family, and then after that family, they have a certain amount of variation. And then you can try to fit the parameters for how many families, where the families are, what the variation is, and so on. Okay, and so this is one very natural thing. It's very much what people do in probabilistic machine learning and in statistics and so on. So this is something that we will not cover. Okay, so this will not covered here. But you will see this is like what people call mixture models, in particular because, in order to talk about modeling in this way and fitting the model, we really need a probability theory, and this really belongs in the realm of statistics very much. And so you'll probably see versions of this in statistics, maybe even already this semester. But another thing we can do is try to reduce to do what's called dimension reduction. Okay, so modeling the data sort of, one could argue requires you to know something about it, right? So and here in sort of this setting, we really want to think about cases in which we have endpoints, we really don't know much about them. And so another thing you can do is dimension reduction. Right, so the idea is to try to replace these points by points in a smaller dimension, right? So try to reduce, say, reduce D, say to, for example, for example, 2, right? So if I have points in the dimensions and I find some way of transforming them into points in 2 dimensions, right, then I can actually draw them. Then I can start making pictures like this on the left. And maybe then I see all sorts of interesting phenomena showing up because I start being able to visualize it. Or maybe by reducing the dimension, right? So by going from sending these points from RD to some RD prime, where D prime is much, much smaller than D, then maybe I start seeing structure and starts being much, much easier to then use other algorithms or even directly learn something. Okay, so this we will cover. Okay, so this will be sort of one of the first topics. Okay. Another thing you can do is try to cluster the data. Okay. And the idea here is, well, maybe I don't know anything about the data points, but when I look at them, they look, I draw them. Again, I can only draw in 2 dimensions, but you can imagine how, you could do things like this in much higher dimensions. But let's say that you draw these points and you see that they look like this. Right? And if you're able to draw them and you see this picture, then it's probably very, you would immediately think, well, probably this is one group that corresponds to a type of data points, and this is another group, and it would make sense to split it into clusters. And so this will cover as well. Okay, so we'll cover these two forms of unsupervised learning. And clustering is a bit, dimension reduction is much richer mathematically. So we'll spend most time on this, and this will be what we'll do next week, right? So mathematically rich. Okay, and this, if you've heard words like truncated SVD, PCA, and even things like isomap and TSNE and things like this, they're very much in this category. We'll focus very much on the linear aspects of it, in particular with truncated singular value decomposition and so on. Now, depending how much time we have, I mean, it also depends on how fast we can go and so on. It turns out that these two approaches can be viewed as sort of two faces of the two sides of the same coin, because in a way, both of them, what you're trying to do is learn the geometry of your data, right? You get these point clouds, these endpoints in the dimension, and in both of these settings, what you're trying to do is learn the geometry of your data, right? So they're both about sort of learning geometry of the data. Where on the first one, the geometry is that it actually naturally belongs or naturally projects to a low-dimensional space. So its intrinsic dimension is sometimes is in some form smaller. And the second one is that it splits very well into clusters. Okay, and so now you can try to postulate that there's all other kinds of geometries that you might be interested in learning. Maybe it is, if you've taken some differential geometry, maybe this data belongs to a low-dimensional manifold, but not one that's necessarily linear. And this gives rise to something called manifold learning and so on. About that, we won't talk as much, but depending how much time we have, I might say a few words. Okay. Another side of unsupervised learning, which we will cover if we have time, is instead of having endpoints, you might be given a graph, right? So another setting of unsupervised learning is when one is given a graph or a network. So, oh, I just saw there's someone in the waiting room. Can one of you? Okay, perfect, thanks. And so when one is when one is given a graph or a network, so what does that mean? You have data points, but we can still think of them as x1 and xn and so on, but now they're not necessarily, they don't live in n dimensions. What they are is vertices of a graph, right? So maybe we have node 1, node 2, node 3, and they have connections if they look very similar, or if they're connected, if you think of some kind of social network or protein-protein interaction and so on. And so instead of having sort of coordinates for each point, what you have is interactions between them, right? And so you can still do unsupervised learning in that sense, right? You can do actually both of the things that arise above. You can say, can I go from a graph, from a network? Can I move these points to RD? Right? And this gives the very, I mean, in a way, spectral graph theory attempts to do this, or you can ask how to cluster a network, or to cluster nodes of a network. Turns out that this is quite mathematically rich as well, and this gives rise to something called spectral graph theory, or you know, the right tool to answer some of these questions mathematically is so-called spectral graph theory. This we will cover in as much depth as we have time. We will see. Okay. So this is what unsupervised learning will be about, right? So this will be sort of 25% of the course. Okay. Okay. Any questions about what we'll cover here? If not, then I'll go to the next step. Okay. So next we have something that that I'll call a data parsimony, or maybe we should think of it as sparsity. Okay, and this is a bit different. Maybe a very good I'll start with a very nice example in recommendation systems. But the point is that sometimes sort of what we want to learn. So here we got points, and we want to understand its geometry. We knew nothing about these points, and we wanted to understand the geometry of them. But here is more the setting where we know some structural properties of what we're trying to learn, and we want to exploit these structural properties to learn it effectively. Okay? And so one of my favorite examples is the so-called Netflix problem. So the Netflix problem, which many of you maybe have heard of, right? So this is maybe, I don't know, maybe 10, 15, 15 years ago, where and it was a sort of, there was a prize, and teams could compete and so on. I'll talk a bit more about this when we actually get to this topic. But the idea is that if you think of the Netflix rating matrix, so Netflix actually doesn't have ratings quite the same way as they did back when they had their Netflix problem. But if you think of ratings of items, so maybe you think here this corresponds to movies, right? So there's a movie here, like each column corresponds to a movie and each row corresponds to a user. And maybe the user watches a movie and puts its rating, right? So this is the matrix of ratings. So it turns out that these matrices are low rank, okay, or at least well approximated by low rank, or almost low rank, I should say. Okay, but let's put that in the log for now. We'll talk more about it when we get to this topic. Okay, so if you were to put the ratings, if you made a big matrix with movies and users and rated the movies, I think back when this prize was up, was the Netflix ranked at 1 to 5. Then the Netflix engineers said that the rank was approximately, I mean, I don't remember, but we're talking about something like 10 or 15 or something like this. Or maybe definitely no more than 100, while the number of users in movies is, of course, much bigger than this. Right? And so the question is, what can we gain from the fact that we know that this is low rank? And in fact, in particular, what can we gain? What do I mean by this is that, of course, Netflix doesn't have, not every user has watched every movie. So they have some ratings. They know what some users like that watched and decided to rating. So they have some entries filled up. But now they have a user who's willing to go watch a movie and they don't know what to suggest. So they want to know for a movie and the user, they want to know what is the rating that this user is going to give this movie even before they watch it, right? Because then they can make better recommendations. And so the question naturally here is, can we complete a matrix if we know it is low rank, right? And in particular, how many entries we need to sample, let's say at random. So here I'm going to need a little bit of probability, but really not much. Need to sample before we can complete the rest. Right, so clearly if I have no hypothesis whatsoever in the matrix, I need to really get the ratings of everyone. But it's clear, I mean, you very quickly will realize that if I know the rank is 1, if I give you, one column and I just give you an entry of the second column, you can fill in the rest of the column. Right? So this is known as, recommendation systems work very much in this way. Now, the mathematics of recommendation systems is trickier and it's a bit deeper. So we'll focus on a setting which is actually very close in spirit, and for which the mathematics are simpler and more transparent. And then we will make some analogy to this problem, but really an in-depth study of the problem of matrix completion. And so this is known as matrix completion. Will have to be left for the master's class. The version, however, that we will be able to do in this class is of sparsity. Okay. So for reasons that will become more apparent in a few lectures, the problem of completing a low rank matrix is very close to that of learning a sparse vector via linear measurements, right? So you can view, low rank as being when you take the eigen decomposition, or in particular, because this matrix is not square, the singular value decomposition, it will have many zeros, right? Many of the singular values will be 0. And so this turns out to be related to the problem of exploiting sparsity in say signal processing and data science and so on, right? And this is known as compressed sensing. And the mathematics of this are very nice. And once you really understand compressed sensing, going to matrix completion is much easier, even though it requires some more deep mathematics that we can't cover fully, but I'll describe in the end how to make the jump. So here, the best way to think of this is you have a vector x. Think of it in very high dimensions. I'll try to use d for dimensions, and I'll try to write big D if the dimension, if I want to like emphasize that the dimension is very big. Okay, so you have a vector x in very many dimensions, but you know it's sparse, right? So you know x, say, is S sparse. So what does this mean? This means that x only has S non-zero entries. Okay? And the idea is that S is much smaller than D. Right? I mean, you probably have seen this already, but if you take a picture with your phone or a camera or anything, right? If you were to save it in, I think it's called BMP, right? So where you literally, you take a picture with whatever many megapixels your camera in your phone has, and if you ask if you try to save it in BMP, what this means is you're asking the computer or the phone to actually save the value of each pixel, and this occupies quite a bit of space. And then if you switch it to JPEG, it occupies much less, right? And JPEG is exploiting the fact that the image as a vector is sparse. Now, you might already be asking, what do you mean the image is sparse? The image doesn't have zeros. That would correspond to black parts of the image, and I take pictures that have no black part to it. Most of the times, you're taking like right during the day of a landscape. It is sparse in another basis. So if you write it in the, for example, the wavelet basis, or in the case of JPEG 2000, it's the wavelet basis. In the case of sort of the JPEG, the older JPEG, which I think is still in use quite a bit, it's just the Fourier transform over blocks. But the point is that there is a basis. If you write in other coordinates, not the pixel coordinates, then it is sparse. And so then you only save the non-zero coefficients and their locations. This is much cheaper. But the interesting question arises as if I know it's sparse, can I actually recover it from a lot less measurements, right? And so it arises the question of if I get linear measurements of it, so if I get AX equals Y, if I get the vector Y, and here it's useful to think about what the sizes of this is. So guy will be in Rm, say, okay. This will be equal to a short fat matrix, right? That will have, I'll do this sometimes where I put the sizes just so that we keep them in mind. D is much bigger than M. X is our sparse vector. Okay. And so I'm getting, we know from linear algebra, numerical linear algebra, and so on, that if I want to be able to solve a linear system, I ought to have as many, right? I ought to have my matrix be square and then singular and so on. So I ought to have as many measurements as I do vectors. But here we know that the vector is as sparse, right? In particular, if I knew exactly what coordinates it was 0 and what coordinates there weren't, then certainly I would only need M to be S, right? But the point is I don't know. I know that the vector is as sparse, so we'll have some non-zero components. I don't know where they are. Another question is, can I recover? So can we recover X from Y? And turns out that this has beautiful mathematics in it, connecting with many things in linear algebra and signal processing and so on. And then the things that we develop here are the ones that are used for matrix completion, and I'll be able to draw the analog with matrix completion without really proving everything in matrix completion, because this requires sort of deep probability theory. But in this case, I can avoid the probability theory. Okay, so this will be part 2. Okay, then I'll talk more briefly about parts 3 and 4, because then Nikita, when he starts, he can give you a longer overview of his parts. But the other 2 parts correspond to supervised learning. So we saw unsupervised learning, right? So what is supervised learning? And so supervised learning is when you get data points, but you have some label about them, right? Think like regression, which you haven't seen yet. You'll see in statistics this course, right? Here will be a bit different than regression, but right, I have some data points x1, x2, x3, x4, right, x5, and so on. Right, say x6. And the idea of supervised, think of them as pictures, for example. Right? And the idea of the supervised learning is that you also have labels. So maybe you know that picture x1 is a picture of a cat. right? And picture of x2 is a picture of a dog, right? Picture x3 is another picture of a cat. Then you have another picture of a cat, and you have a picture of a dog, right? So you know what these are pictures of cats and dogs, okay? And now the question that supervised learning is interested in is I give you now a new image. Can you tell me if it's a cat or a dog, right? Can you learn what is a cat or a dog? It's not just about learning the geometry of the data, right? It's not just about learning geometry of, of, of pictures and of the data, but really about learning the function that goes from the pictures to what it means to be a cat or what it means to be a dog. Okay, and so here this supervised learning has beautiful mathematics. Here we're going to start needing a little bit of probability theory, and but we're sort of going to introduce everything that we use. And basic things like linearity of expectation and so-called concentration of measure. So there'll be a class or half a class just introducing, the simple inequalities of concentration of measure. For those who know, think like Chernoff bounds. Okay, it's just this phenomena that I'm sure many of you have seen that, if I flip n coins and I count the number of heads, then I'm going to get around n over 2, and I can measure actually how close to n over 2 usually I get, and what's the probability of getting many more, many less than n over 2, and so on, right? So we'll need a few of these things, but we'll like what we need, and so we'll talk about generalization, right? So what is generalization, right? So maybe I don't want to talk much. Yeah, I don't want to spend much time talking about supervised learning for now. As Nikita will then give an overview when it starts. But you should think of this as you're learning a function that goes from images, right? You're learning a function that goes from images to being a cat or being a dog, right? And now you try to come up with some function, like you come up with some fancy function or computer program that given an image tells you if it's a cat or a dog, and you try it on these 5 examples. And you say, I get perfectly correct. You say, great, I now understand what it means to be a cat. But really, this doesn't mean that when you get a different image, that it actually is going to get it right. Right? And so the idea of generalization is to try to understand when is it that by training something on a training set, right? This would be what people call a training set. When is it that it works on what's called a test set? Right? And here, one of the key ideas is basically goes back, to the so-called Occam's razor, which is that you're more likely to. I mean, we all have this intuition in our minds, even before we study any math. The simpler your function is, the more likely you're going to succeed. If you find an extremely simple function that works for many examples, probably will also work for the next one. If your function is very complicated, a bit less likely for it to work. Right? This is certainly an intuition that makes sense, and there's this whole notion of overfitting and so on. And so what we'll do is we'll actually make these intuitions a lot more precise. And what is one way of trying to do this? First of all, you need to have a way of measuring what it means for a function to be very complicated or not, right? And so we'll talk about things like VC dimension and so on. Maybe another way of thinking about this is if I write, so I think this is useful to have in mind. If I see let's say that I again put the images in 2D, right? Sorry for only being able to draw in 2D, and you have cats. And now I have also images of dogs, right? For whatever reason, I draw them in 2D, and they look like this. And now I ask you, okay, now you get a new image, and you see that it's this one. Right? I mean, I think everyone would probably say, yeah, this is probably a dog. Right? And how can you make this precise that indeed, somehow you're pretty confident that this should be a dog? Right? There's a couple ways. One is to say, well, these seem linearly separable. So like this very simple rule of cat goes here, dog goes here seems to work. Right? But how do you make this precise? One is through the ideas of VC dimension, of measuring what it means to be simple. Another is a very nice trick, which I think is known as stability, or this one way, which is that the fact that I got these cats and dogs I came up with this very simple rule, right? Then if this red one was actually a cat, then I could think of instead of, right, let's say that for whatever reason this was actually a cat. Then if I were to think about solving this problem where I receive, so I mean, I don't know, 1, 2. So I have 16 images in total. You got 15, learned something, and then tried on another one. But they should come sort of from the one that you received later should be of the same type of the first one. So you could have said, okay, so why don't I have my simple out procedure in how to do this? What if I had received 15 other images of these 16, and the one I had to predict was, another one, maybe this one? Then the other 15, such a simple estimator wouldn't have worked, right? Because it was a cat in the middle of the dogs. In fact, most of the other choices of 15 to train on and 1 to test would have sort of jumped, like you would have been worried because you say, oh, this doesn't look right, right? And so you can make this into a mathematical argument to argue that if the data looks right, then the next point, should look good too, because otherwise you would have already probably seen one that also looks bad, right? So I'm trying to say this without any mathematics because I don't want to do it on the first, I don't want to introduce any notation and so on the first class for now. But turns out that this idea can be mathematically rigorous, and Nikita will do it, and it's a very powerful one, and it's related also to VC dimension and so on. Okay, now last but not least, and here, okay, so there'll be a lot about the mathematics of generalization, but how do you actually come up with functions to try? You can come up with linear separators and all this. But of course, these days, what people do is they use neural networks a lot. And so if there's time, we'll talk a little bit about neural networks, but how much we can talk about neural networks, given that we're mostly talking about mathematics, and at this level is actually very little, probably only things that you already know. And so this is only if time permits. Now, so last but not least, and I mean, I'll be very brief here, is, and then we'll take a break, is online learning. So this will be the last part of the class. And online learning is about, this is also called as streaming. So what if you want to make decisions, so learn from streaming data. Right, so the point is you're doing, say, learning between cats and dogs. I mean, more interesting examples would be if you're sort of maybe managing a portfolio of stock or doing real-time auctions for ads on the internet or things of this type, in which you gather data, but you have to make decisions of, what stocks to hold in your portfolio or how much to bid on the ads. And as you make your decisions, you gather more data and you have to update your decisions and so on, right? And so the setting changes a bit. Then all the settings above, you first get to see all the data, just all the data falls in your lap, and then you decide what to do. Here, you have to decide as the data comes, and in fact, sometimes even your decisions might affect which data you get. And so this here, we'll talk, so this is very useful for, say, portfolio management, right? Portfolio updates, like ads, ad auctions. And so the interesting things that we can do here are things like learning from experts. There's some really beautiful mathematics there of if you have, say, many experts telling you which stocks are best, can you come up with an online strategy that does at least comparable to the best experts, say, or things of this type? So it turns out that this is possible, and there's very, very nice mathematics around it, like learning from experts, things known as multiplicative weights, and so on. And here, depending how much time, it will also be when we'll talk a little bit about optimization. Right. And so, and perhaps gradient descent. And if there's time, a little bit about even like explaining backpropagation, but I assume probably many of you have seen this, which is how neural networks actually get trained. Okay, so if there's time, backpropagation. Okay, so this will be the course. We'll focus on the mathematical sides of this and proving theorems and so on. And yeah, I think this is the plan, but we'll see as we go at which speed we go, depending on the feedback that we receive. We can slow down, speed up, change topics slightly. We have some flexibility. Okay, so I guess we should take a break now, but I'm happy to take any questions.